Welcome back. We are now going to discuss the chapter on estimation, which is a very important part of statistics and machine learning in general. So I'd like to begin this discussion with a question. And so the question is, how do you find the parameters of some distribution? So we just did a review of random variables, and in every problem we did in chapter 3, chapter 4, the problem started out with something like, assume you have an exponential distribution with a certain lambda. So the problem just gave us the lambda, gave us the parameter. But in real life, that's not the way things work. In real life, we have a data set, and we can infer what sort of distribution it is based on the type of problem it is often. But that distribution has some set of unknown parameters, and we have to estimate them. So as a concrete example, let's say that x is a random variable indicating the time until failure of some part. And let's say that we can assume that this failure time has an exponential distribution. So if you remember from 2 chapters ago, this is the PDF of an exponential distribution. It's a function of one parameter, one unknown parameter, lambda, and we've observed 15 parts until they failed, and here are the actual observations. So the question is, where do we get lambda? So I hope that you can kind of appreciate the problem that we're going to deal with here. Now, we've dealt with a lot of estimation problems already. So we've had things like binomials, and binomials have a parameter which is the probability of a head, or probability of a success. And I'm going to say that the estimate, so just take the number of successes over the number of trials, was kind of obvious. But obvious isn't going to be good enough for us. We need a better rationale. We need a systematic way of getting to number of successes over number of trials. Now, in the exponential case, it's not at all obvious what we should do to figure out what this lambda is. So what we're going to see is that there's not just a simple way as there is with a binomial to estimate the parameter. Often there can be multiple ways to estimate parameters, and that's going to raise another question, which is which one is better, which kind of brings us to an even bigger question of how do we evaluate estimation approaches in general. So what we're going to do in this chapter is really 2 parts, and these parts are somewhat theoretical, but again, you're going to use this all the time in machine learning and statistics, so it's really important to understand these concepts. So the first question is going to be, what are the properties of estimates? And so we're going to discuss a lot of things that would be nice to have, like unbiased. What does unbiased mean? Minimum variance estimators. What does that mean? Minimum mean squared error estimators. What does that mean? Then we're going to move on and talk about different methods of estimation. And these methods of estimation will have certain properties that we discuss in this first section. So let's go to the next slide, which is our definitions of different estimation properties. So we tend to use theta hat as our as a generic estimator. So theta hat is just some estimator of a parameter theta. Now you can plug in any specific estimator. For example, you could say let x bar be an estimate of parameter mu, or let s squared be an estimate of parameter sigma squared. But in general, we're just going to refer to the estimator as theta hat and the parameter that's being estimated as a theta. So two of the most important properties of an estimator are the mean and are the bias and the variance. So what is the bias? Well, the bias is simply what is the expected value of this parameter minus the value of the parameter. So this is on average, what is the statistic going to produce? This is the true parameter. Then the variance of the estimator is just saying, well, how far do you think you're off in squared units? So what is the expected value of theta hat minus its mean? So on the average, how far am I from the mean of this distribution? So another definition is unbiased. So a statistic is said to be unbiased when the expected value of that is equal to theta. So I think we need to do an example. Let's say that we have a random sample, x1 through xn. So we have a random sample of size n, and we're going to assume that the true mean of this from the population is mu, and the true variance is sigma squared. The result that we want to establish is that both x bar and s squared are unbiased estimators of mu and sigma squared. So let's go establish this off on paper. I think sometimes it helps to see these things in paper. So let's just remember what our given was. And so the given is that we have x1 through xn, and it's a random sample. So random sample. And we've been told that the mean of each one of these x's, so let's just write e at xi as the mean, is some parameter mu. And the variance, so let's write this as the variance of x sub I is equal to sigma squared. And you can write for all I if you want. Now, let's write out what we're trying to show. So I always like to say WTS for want to show. And so we want to establish that the sample mean, so x bar is the sample mean, and that's just the sum of my xi's divided by n, that the expected value of this x bar is equal to mu. So that's what we're trying to show. Well, this is a very easy thing to show. So let's just go do that. So what's the expected value of x bar? Let's just start on the left-hand side and see if we can get to the right-hand side. So this is equal to the expected value of 1 over n sum xi. Now, remember we had a result last time. The expected value of, what was it, ax plus by is just a e at x plus b e at y. All right, so if you've got multiple random variables and you've got some constants out in front, so think of this as a constant, that's like an a or a b, I can pull those constants out in front of the expected value sign and just distribute the expected value sign over my random variables. So let's go do that. This is going to be 1 over n. Then I can bring the expected value sign inside. So I'm just going to write the limits of this sum explicitly so we don't forget them, times the expected value of x sub I. Well, what is the expected value of x sub I? We've been told that the expected value of an x sub I is a mu, and it's a common mu across all my observations. So we don't need a subscript there. So what is the sum from I equal 1 to n of mu? I just have n copies of mu. So this is going to be 1 over n times n mu, and notice my n's go away, they cross out, and we're left with simply mu. So we've now shown that on the average, my x bars equal mu. And so we saw a concrete example of a sampling distribution last chapter, where I remember we had 3 units in the population. We generated all possible values, and sometimes the estimates x bar were too big, sometimes they were too small, but on the average they were right. So this is a proof of that result. Well, let's go work on the second result that I said we would establish. So let's say that s squared is our sample variance. This is just 1 over n minus 1 times the sum, I equals 1 to n, xi minus x bar squared. And we want to show, so let's just write that over here, want to show that the expected value of s squared is sigma squared. Well, this one, to be honest with you, is going to be a little bit more involved. So I want to establish a couple things before we try to establish the main result. And so what I'm going to do is start out with this thing right here. Okay, so this thing right here, we're going to have a special name for shortly. We're going to call it the total sums of squares, or the sum of squares total. And so let's go write this out. So this is xi minus x bar squared. So let's just work on this inner piece and try to, put this in a different form that's going to make our life easier. Now, I'm going to do a little trick that is very often done. So it's a good trick to know about, and that's why I'm dragging you through this proof, or this derivation, whatever you want to call it. So what I want to do here is add a mu and subtract a mu. So I'm going to write it like this, just to kind of keep my number of steps down. So xi minus mu, and then I'm going to have x bar minus mu. So look what I have here. I have a minus times a minus gives me a plus mu minus a mu. So really, I've just added 0 to an expression, and when you add 0 to an expression, it doesn't change it at all. So what's left is xi minus x bar, and that's what we had before. Well, let's go expand the square on this. This is equal to the sum of xi minus mu squared. So if I just square this first term, that's what I end up with. Now we have to take minus 2 times this, summed. So what I'd like for you to notice is the second quantity here has no subscripts in it. So I can pull that out. I can use the distributive law and pull that out. So this is going to be x bar minus mu times the sum of, well, xi minus mu, and there's no squared here because that's the middle term. And then I'm going to square this last term. So let's just go plus the sum of x bar minus mu squared. All right. Well, I'm going to give myself a little bit more space here in the next set of equal signs. This is going to be xi minus mu squared. So we're not going to touch this first term. And then let's go play with the second term a little bit. We end up with 2 times x bar minus mu. And then what do we have here? We have the sum of xi, and then I have the sum of mu. So this is the sum, I equals 1 to n of mu. So that's just n times mu. And then let's go see what we have here. This is the sum, I equals 1 to n, and notice there's no subscripts, so this is just plus n times x bar minus mu. All right. Well, let's carry on here. Xi minus mu, I'm not going to touch this first term at all. Let's go look what I have here. I want to rewrite the sum of xi. The sum of xi is really just n times x bar, right? So if we go look at what's my x bar, if I multiply both sides by n, the sum of xi is just x bar times n. So that's what this piece is. So what I'm going to do is I'm going to factor out an n. So let's just go factor out that n. This is just 2 times n. And then I'm left with x bar minus mu times x bar minus mu. So that's just x bar minus mu squared. And then this last term is plus an n times x bar minus mu squared. So believe it or not, we're actually making serious progress here. So this is xi minus mu. Again, I'm not touching that first term. And notice what happens here. This is x bar minus mu squared, x bar minus mu squared. I have 2n of these. I have a plus n of those. So this is going to be minus n times x bar minus mu squared. All right, that's a really important result. Now, let's go take the expectations of both sides. So the expectation of this thing is, well, xi minus x bar squared. Let's make those square brackets. And this is equal to the expectation of the sum of xi minus mu minus n times x bar minus mu squared, and close your brackets. Well, let's go distribute our expected value sign. So this is equal to the expected value of, actually, hold on. I'm going to make this the sum. We're going to pull the sum out. I equals 1 to n of the expected value of xi minus mu squared. So all I did is I pulled the sum out and moved the expected value sign into this thing. And then I have n times the expected value of x bar minus mu squared. If you want, you can put brackets around that. Well, what do I have here? What is the expected value of xi minus mu squared? Well, that's just the definition of variance. This is just the variance of xi, which we've assumed is sigma squared. So I'm going to go write that up here. Well, let's go see what we have here. What is the expected value of x bar minus mu? Let me refresh your memory that the expected value of x bar, actually it's up here, the expected value of x bar is just mu. So this is just the expected value of x bar minus its mean, but that's then just the variance of x bar. What's the variance of x bar? Well, last week we learned this was sigma squared over n. Okay, so we're really getting somewhere now. So this is equal to, I've got the sum from 1 to n of sigma squared. So that's just n sigma squared. Then what do I have over here? I have n minus n times sigma squared over n. Well, the n's cross out. And we're left with n sigma squared minus 1 sigma squared, which is n minus 1 times sigma squared. All right. At this point, we're ready to establish the thing we were trying to establish. So let's go do that. Believe it or not, I don't have much space left on this paper, but having done all the work that we've done, this is all the space I'm going to need. So what is the expected value of s squared then? Well, the expected value of s squared is equal to 1 over n minus 1 times the sum of xi minus x bar squared. So there's the definition of s squared. But I can pull this constant out. So this is n minus 1 times the expected value of this thing. Now, what's the expected value of this thing? It's sitting right here. So times n minus 1 sigma squared. And notice my n minus 1's go away. And we're just left with sigma squared. So what we've just shown is that on the average, s squared using this n minus 1 denominator gives us the correct variance. So therefore, both s squared and s squared and x bar are unbiased estimators of their respective parameters, which is what I wanted to show in this theorem. All right, moving on. Among all estimators of some parameter, the one that has the smallest variance is called the minimum variance unbiased estimator, the MVUE. And so these are going to be desirable. You know, we could potentially have two estimators, and one of those estimators would have a higher variance than another one, and that would be undesirable. So just to show a quick example of this, let's go back to my my paper here, and I'll give you an example. So let's say that we have a random sample of size 2. So let x1 and x2 be a random sample from some population with the expected value of xi in both cases equaling mu, and the variance of each xi equaling sigma squared. And I'm going to say this. Consider two estimators. All right, so estimator 1, let's just call it x bar, is going to be x1 plus x2 over 2. And my other estimator is, let's just call this x bar w, which is, let's take 1/3 times x1 plus 2/3 times x2. So we're going to give x2 a little bit more weight. So what I'd like to show you here is that both of these estimators are unbiased. So both are unbiased, but x bar has smaller variance. So let's just go see this. What is the expected value of x bar? Well, it's equal to the expected value of x1 plus x2 over 2. I could just point to what I had on the previous slide, but sometimes it helps to see it written out. This is just 1/2 times the expected value of x1 plus the expected value of x2. And so what is this? This is 1/2 times mu plus mu, which is mu. So sure enough, x bar is unbiased, just as it was on the previous page. What's the expected value of my weighted mean? Well, the expected value of my weighted mean is this: 1/3 x1 plus 2/3 x2. So you can see how this is going to work out. This is 1/3 mu plus 2/3 mu. There's a mu there, is equal to mu. So both of these, both are unbiased. Let's now go find the variance of these two estimators. So what is the variance of x bar? Well, it's going to be the variance of x1 plus x2 over 2, which is going to be 1/4 times, what's the variance of x1? Sigma squared plus sigma squared. So this is equal to sigma squared over 2. Well, let's go find the variance of the other estimator. So x bar w. So this would be the variance of 1/3 x1 plus 2/3 x2, which is 1/9 sigma squared plus 4/9 sigma squared, giving 5/9 sigma squared. So notice 5/9 sigma squared is greater than 1/2 sigma squared. So note 5/9 sigma squared is greater than sigma squared over 2. So x bar is a better estimator of mu. So we would prefer this estimator, x bar, over this one in this setting. Now, I'm going to give you a similar problem in homework, but what I'm going to do is change it so that the observations have different variance. And so what you'll see is if the variance of x2 is in fact smaller than the variance of x1, then it would make sense to give more weight to the more reliable case than to the less reliable case. And so if you had a situation where not all of your observations have the same reliability, then x bar w can actually be a better estimator than x bar. And so I'm going to ask you to show that on the homework assignment for this week. All right, that's enough for bias, variance, and unbiasedness.